Hi everyone. In this video, we're going to look at a second method for calculating volumes of revolution, and that's the shell method. So let's look at an example where we would want to use the shell method. So we've got a region bounded by a quadratic. So this quadratic has its vertex at 1, 1. And so it's going to look something like this. And that is going to be at 2. All right, x equals 2. So we would want that intersection, which is going to be 2, 2. And x equals 4. So we would also want that intersection. This is going to be at 4, 10. We have the y equals 0, so the x-axis. So the region that we're talking about here is this region right here. And we are wanting to revolve it around the y-axis. So the region is formed on the x-axis, but I'm wanting to revolve it around the y-axis. And that's possible using the disk method, but it is a little tricky. So typically speaking, for the disk method, I'm going to want to define a region on the y-axis. So I can do that here. If I think about, I'm going to sketch what this would look like. So if I just revolved the line x equals 4 around the y-axis, I would end up with a cylinder. So I'm going to end up with a cylinder whose volume I could calculate. And using the disk method, I would then define this region right here and subtract that out of the volume of the cylinder. But I would actually have two regions because I would have to divide. I'd basically be looking at the fact that between 2 and 10, I would have sort of this bowl-like shape being pulled out of the cylinder. And between 0 and 2, I would actually just have another cylinder inside of my cylinder. So I could figure out this volume by breaking the shape into those pieces, figuring out, okay, so I've got in this diagram, the y-axis is here. So I would know, for example, that this height here is a height of 2, that for this outer cylinder, I've got a height of 8. The radius of that cylinder is 4, so I can figure out the volume of that cylinder. The radius of this internal cylinder is just going to be 2. So all of those I can figure out without using calculus at all, because I can just use the formula for volume of the cylinder. And then the bowl section, I would have to use a volume of revolution in which I rearrange that function so that it's a function of y instead of a function of x, because I'm going to have to integrate with respect to y, because when I draw that little rectangle, it's dy. So that is entirely possible using the methods that we have already learned, but it's tricky. So instead, we have this second method where if I want to rotate around the axis that is perpendicular to the axis where my region is defined. So in other words, it's way easier here for this region to define a rectangle perpendicular to the x-axis. So in other words, I have a rectangle that is parallel to the axis of rotation. So I still want to integrate with respect to x, but on the y-axis. So if I imagine what shape that forms, when I just take this little slice, this little red rectangle that I've drawn, and I revolve it around the y-axis, that's going to form a tube. So when I revolve this around, it forms a tube. I think of it like a toilet paper tube. And if I take that toilet paper tube and I slice it open and unroll it, I've got a rectangle. Well, technically a rectangular prism because it does have some thickness, but we want it actually to be very, very skinny. So that thickness of that rectangular prism is my dx. So thinking about that rectangle, the height of the rectangle is going to be y, because that's the height of the little slice that we've pulled out of this region. And like with any cylinder, so thinking surface area of the cylinder, this is going to be the circumference of the circle. So the circumference of the circle being 2 times pi times the radius, but the radius is the x value. So 2 pi x is the circumference, which is what ends up being the width of that rectangle. So the volume of this little tube that we created is 2 pi times x times y times dx. Well, that means that the overall volume of the solid of revolution is the sum of all those infinitely many tubes, so the integral. So the volume is the integral from x equals 2 to x equals 4 of 2 pi xy dx. So when we're using the shell method, that's our formula. It's 2 pi xy dx. Well, in this case, y is actually defined in terms of x. So in this case, the volume is from 2 to 4. I'm going to actually put the 2 pi up front because that's just a coefficient. X times y, which is x minus 1 squared plus 1, dx. So let's distribute all that and figure it out. So 2 pi, 2 to 4. All right, so x minus 1 all squared is x squared minus 2x plus 1. So I've actually got x squared minus 2x plus 2 inside these brackets, which means I have x cubed minus 2x squared plus 2x dx. The antiderivative of that, just applying the power rule, I've got x to the power 4 over 4 minus 2x cubed over 3 plus x squared, evaluated between 2 and 4. So if I evaluate that at 4, so 4 to the power of 4 over 4 minus 2 times 4 cubed over 3 plus 4 squared all ends up being 112 over 3. And when I plug a 2 in there, 2 to the power of 4 over 4 minus 2 times 2 cubed over 3 plus 2 squared, I get 8/3. All right, 112 over 3 minus 8 over 3 is 104 over 3 times 2 pi. I get 208 pi over 3. That is the volume. So this is an example of when I would use volumes by shells. All right, so just to summarize, we basically have 4 different scenarios. So let's look at the 2 scenarios where we are rotating around the x-axis. So I want to rotate around the x-axis. Well, then I have 2 possible situations. I have a situation where I have a function that I can define in terms of x, so y equals f of x, and the region that I'm talking about goes from a to b on the x-axis. So if my function is defined as a function of x, and the region that I'm wanting to rotate is on the x-axis, in this case, the slices that I would draw, the rectangles that I would draw, are perpendicular to the axis of rotation. So I would draw these rectangles, these slices, they would be dx. So this is a situation in which I would use the disk method. In other words, the volume here would be pi times the integral from a to b of y squared dx. That's the disk method. On the other hand, if I'm wanting to revolve around the x-axis, but I have a region that is more properly defined in terms of y, so x equals f of y. In other words, I'm looking at a region that is on the y-axis, but I want to rotate around the x-axis. So this region right here, remembering that we might have an inside function and an outside function that we have to find volumes and subtract. But if it's more logical to draw my slices parallel to the axis of rotation, in other words, to use a dy, then this would be a case for shells. And that would mean that the volume here is 2 pi times the integral from a to b of xy dy. So those would be the 2 situations if we're rotating around the x-axis. Now, if we want to rotate around the y-axis, this kind of gets reversed. So if I want to rotate around the y-axis, but I have a function and a region that are defined on the x-axis. So something like what I just drew above, if I've got y equals f of x, I've got boundaries on the x-axis, but I want to rotate around the y-axis. So the region is what I'm shading here. So it makes more sense to draw a rectangle that is perpendicular to the x-axis. In other words, to use dx. If I'm using dx here as a vertical slice, but I'm rotating parallel to that axis, then this is a situation where I would use shells. In other words, the volume is going to be 2 pi times the integral from a to b of xy dx. And the final situation, again rotating around the y-axis, but in this case where I can define x as a function of y, and the region is on the y-axis. So I'm rotating around the same axis that my region is defined on. So here's the region. In other words, it makes the most sense to take my slices perpendicular to the axis of rotation, which in this case would mean I'm using rectangles with a width of dy. If my slices are in the same variable as the axis of the rotation, then this is a disks situation. And my volume is going to be pi times the integral from a to b of x squared dy. In the cases of disks, we're basically using the formula for area of a circle because the shapes that get formed are disks, so in other words, circles. And for the shell method, we're basically using the formula for surface area of a cylinder because the shapes that get formed are tubes, which are like the surface of a cylinder. There is a worksheet for this in D2L.